Welcome back to more math lessons in Algebra 1. As you may notice, the scenery has changed a little bit. I'm back in the classroom, going to take advantage of the smartboard, and we will use it to our advantage, hopefully. This is lesson 85. We are solving problems with the Pythagorean theorem, our old friend. We all understand c squared equals a squared plus b squared. But here's one reason why it works. If we look at two squares, one big square and another square inside that big square. You with me so far? All right. The big square, the points where the little square touch divide the big square into two line segments. B and A, B and A, B and A, and they all are the same. A is the same as A all the way around, B is the same as B all the way around. And the inside square, it's a square, so all sides are the same length. We'll call them C. Okay? So if we look at the big square, the outer square, the area of this outer square would be the length of a side times the length of a side. Well, the length of the side is A plus B. And that would be times another A plus B. And so the area of the big square is A plus B squared. And even simpler, the area of the little square is c squared, c times c, all right? Now, if we look at these triangles that have been made, these right triangles, all right, we can see that one of these triangles is base times height divided by 2, AB over 2, right? But there are 1, 2, 3, 4 of these congruent triangles. So, the area, if we add up all 4 areas of those 4 triangles, would be 4 times A times B over 2, which we can simplify as the 4 triangles add up to make 2AB. All right, you with me so far? Now, look what happens when we take the inside of this whole thing. In other words, we've got the area of C added together to the area of the 4 triangles. And what does that look like? Well, it's going to be c squared, the area of the inner square, plus the area of the 4 triangles, 2AB. And that's going to be the area of the whole thing. But we already know the area of the whole thing is a plus b squared. If we do the FOIL on that, we get a squared plus 2ab plus b squared. So this area, little square and 4 triangles, has to equal the area of the big square. A squared plus 2ab plus b squared, which we got from FOIL. Well, now if this equals that, then we can simplify some things. If I subtract 2ab from both sides, lo and behold, amazingly enough, I get c squared equals a squared plus b squared. What do you know? And if I want to know what c is, I simply take the square root of both sides, and I see that c is equal to the square root of a squared plus b squared, the Pythagorean theorem. Now, what good is that? You want to find the missing length of a side, and since now we're 8th grade algebra, we can deal with radicals and other things if we have to. But if we've got our basic right triangle, and remember this only works for right triangles, all right? Make sure that you understand which is which, all right? What part is what? The legs, the shorter sides are the legs, and the side that is opposite the right angle is the hypotenuse, and it's always the longest side of a right triangle. So if we know 2 of these things, and want to find the missing side length, we can use the Pythagorean theorem here and see that this hypotenuse, all right, and that's important because if we use C as a leg, we'd mess it up. So in this case, we're looking for the hypotenuse as the missing leg, so that would, the missing side, so 1 leg squared plus another leg squared, take the square root of that sum, and what do you know, it's a nice whole number. All right. Life doesn't always give us whole number solutions. That's fine. All right. Here's another right triangle. And again, we see that opposite the right angle, we have the hypotenuse. So in this case, the hypotenuse is 7. We know that, and one of the legs is missing. But we use the same formula. C equals the square root of a squared plus b squared. In this case, though, a squared we don't know. So we substitute in 7 equals and so forth, square root of 4. Now, to get rid of the radical sign, we are going to square both sides. And this is why we're doing this now, because it fits in with the whole idea of quadratics that we've been talking about in the previous 3 lessons. The idea of dealing with squared terms. And nowhere is that more important than the Pythagorean theorem. So when we deal with squares, all right, big deal, we deal with squares. And in this case, 7 squared, 49, is equal to, we got rid of the radical sign because we squared the whole thing, leaving us with what's inside the radical, t squared plus 16. Subtracting 16 from both sides gives me 33 equals t squared. But I want to know what t is, so I got to take the square root of both sides, and t is the square root of 33. Now, you could be picky and say, well, couldn't it also be negative root 33? And strictly algebraically speaking, yeah, it could. But in geometry, having a negative length of a side is kind of ridiculous. So we say that the root minus root 33 is extraneous. We throw it out. It's not realistic. But the square root of 33 for this length of a side is reasonable. All right? Here's another example. In this case, one of our side lengths is a radical. Again, big deal. All right? We have to understand, though, that this length is the hypotenuse, and therefore it'll be here, while we're missing a leg, and that will be here. All right? So again, substituting in for c equals square root of a squared plus b squared, we identify this as a, and that's b, and that's c, and put it in the Pythagorean theorem. And we have 2 radicals, a radical on this side of the equation and a radical on that side. So we're going to get rid of the radical signs by squaring both sides. And when we square both sides, basically the radical just goes away. Remember, that's root 61 times root 61, which is root blah, 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 but that's a perfect square, and the square root is 61. And here, we square this, makes that go away. Now I got k squared plus 25, 5 squared. All right. So now I got 61 equals k squared plus 25, subtracting 25 from both sides. What do you know? I get 36 equals k squared. K equals 6. All right, worked out, even though we started with a radical. Now, another use of the Pythagorean theorem is figuring out whether or not what you're dealing with is a right triangle or not. Remember, a lot of this geometry only works if it's a right triangle. So it's pretty important to understand whether or not it's a right triangle or not. A lot of times the book gives you that little right triangle symbol. But in real life, you're not going to have that right triangle symbol. So to see if you're working with a right triangle, you have to determine that. And basically all it's saying is if c squared equals a squared plus b squared, if that works, then you have a right triangle. All right? So you have a question like, do these side lengths make a right triangle? And they give you 3 side lengths, and the units don't matter, feet, inches, light years, whatever, all right? One length of the triangle is 9, one length is 40, and one length is 41. And just by looking at that, you'd probably say, nah, that's not a right triangle. That's a weird triangle, but, you know, it's not a right triangle, is it? Well, you don't have to guess anymore, all right? If this is a right triangle, then the Pythagorean theorem is going to work. So remember, you got to understand, the longest side, 41, must be the hypotenuse, all right? And the 2 shorter sides, they have to be the legs. So, if this is a right triangle, this should work. 41 squared should equal 40 squared plus 9 squared. Basically the Pythagorean theorem, we're just substituting in. 41 squared is that, 40 squared is that, 9 squared is that. What do you know? it works. You can make a right triangle out of boards that are that long. And your house will stand up straight. That works out pretty good. Well, speaking of standing up straight, another application of the Pythagorean theorem is the idea of the safe ladder rule. You know, you ever climbed a ladder, but if it's too close to the house, it starts to go back on you? All right? Well, there's a rule that says your ladder should be the distance away from the house, all right, should the distance that's safe to go up is 4 times the distance away from the house. So that says if your ladder is 2 feet away from the house, all right, then 4 feet is the highest you want to use your 4-foot ladder. If your ladder, you know, you can get the idea. If it's too close to the house, it's going to flip over and it's not going to be safe. All right. So you have this distance away from the house, which just happens to be, right, A, B, and the length of your ladder is C. All right. So the idea is you should have a ratio of 1 foot away from the house for every 4 feet going up. If you don't, it's not safe. All right. And you may have a problem like that in your homework. But basically, that's just telling you how long should the ladder be if you're going to put it this far away from the house. You just use the Pythagorean theorem. So, that brings us to the end of lesson 85. Your assignment is A to H, 1 to 9. Again, please work so that you get this done sometime within the next week. All right? Some people have been very good at submitting pictures of this. That works fine. All right. Whatever you do, remember to hold on to it. Make a file folder with all your homework in it for math and science, so we don't have any problems of electronic drop-off or whatever. So, we'll see you at the next lesson.